This is lecture 3 of strength of materials. In the previous two lectures, we saw some basic concepts which are fundamental to the subject. These were stress, strain, constitutive law, and the material stress strain curve. Before we go ahead and see a few more concepts, let us solve a couple of problems. These are the problems which are normally seen in competitive examinations. The first problem is like this. There is a pivot which has a pen, and there is a crank or a simple rod attached to the pen, and the end of the rod there is a mass m. This mass is revolving around the pin with angular velocity omega, and length of the rod is r. Now if the cross section area of the rod is A and it is prismatic, we need to find out the stress, the maximum stress in the bar. Now, how do we solve this problem? We assume, and okay, one more assumption is that the rod is massless. Now to solve this problem, first we need to figure out what is the force acting on the bar. So the force in the bar is equal to the centrifugal force. That is nothing but m omega square r. This is a force in the bar, but here r is the total radius of the circle of circumference, or the whole length is the radius of the rotation of the or revolution of the mass. Now this force is acting exactly at the pin, and it decreases as we go ahead, and it becomes 0 at the mass location. So the maximum force is at the pin. So the maximum force, or the maximum stress rather, will be equal to m omega square r upon a. That is the stress in the bar, maximum stress in the bar, and this occurs at the pin. Now this is a very easy problem to solve, but it can be made a bit more complex by doing this simple change, which is, instead of a massless bar, we take a bar of same length r, but the bar has a mass of m, and it is prismatic. Now assuming the area is A again, we have to find out what is the stress in the bar, what is the maximum stress in the bar. Now the case is complex, because now the mass is distributed over the length of the bar. So we first figure out what is the distribution. So the mass distribution, let's say rho, is equal to m upon r. This is the mass per unit length of the bar. Now to find out what is the stress at a particular location, we need to figure out where the mass is lumped. The whole mass of this bar is lumped at the center. Center is at half the length from pin. Now the whole mass is m, and it is, if it is assumed to be lumped at the center, then we can redraw the problem like this. It is exactly like this one, but the radius now is reduced to half. So the force now is m omega square, omega is the rotation speed, multiplied by r by 2, and the stress is m omega square r by 2a. So you see, just by changing the distribution, or rather just by changing from a lumped mass, which is this one, to a distributed mass, which is this one, the stress reduces to 50% of the value. And this is a very important result. It is a very heavily used result in the design of machinery, especially the rotating machines, wherein these kinds of problems occur quite a lot. Now let's see a second problem. It's also a complex problem. Bar prismatic of area of cross section A is hanging under self weight. Assuming that the weight density is gamma, that is equal to weight density we have to find out what is the displacement of the bottommost point here. Let's say this point is P, and assume that the Young's modulus is E. Now, what is the displacement of point P under self weight? Now, how do we solve this problem? Let's say that the length of the bar is L. We take a section which is some distance Z from bottommost point, and we take a differential element there, which is having a height of dz. So we isolate the differential element. This is the differential element. It has height of dz. Area is of course A, and if we draw the free body diagram of this differential element, so then we figure out that there are three forces acting on it. First force is because of the stress at the bottom face. Let's say it is sigma. The second force is because of the stress at the top face. It will be slightly different than sigma. Let's say it is sigma plus d sigma. And the third force is the weight of the differential element. So that is dw. So now we write the force balance. So sigma multiplied by A, that's the downward force, plus the other downward force, which is dw, that is equal to the upward force, which is sigma plus d sigma into A. Now what is dw? dw is nothing but the weight density multiplied by its volume, which is A into dz. So I put that number here. We get sigma A plus gamma A dz is equal to sigma A plus A d sigma. I just expanded this. Now we cancel out sigma A from both sides. So this is cancelled, and this is also cancelled, and we cancel out A also. So we knock out this one. So I get a relationship d sigma by dz is equal to gamma. Now that's an important result, because what it tells is that the stress changes as we go up, and it is obviously it is zero at the bottom because there is no force acting there, and it becomes highest at the top, and the rate of change of stress as we go ahead is equal to the weight density. So why is this happening? Because as we go up from here to here to here to here, we go on adding weight, and every section, like this section and this section and this section, so as we go up, the sections have to take more force or more weight. Now let's see, this is a section which we are studying right now. This is AA, this section AA. Now over here the stress is sigma. Now let's say that the deformation in this small segment is d delta. That's a deformation of that small differential element, or let's say that's a change in the length of its original length. So the dz becomes dz plus d delta. So the small amount of strain which is there in that bar in the differential element is equal to d delta by dz. That's a strain in that. Obviously, from the Young's Hooke's law, we know that sigma is equal to E into epsilon. So in this case, it becomes sigma is equal to E d delta by dz. Now we feed in this value of sigma here, we get d by dz E d delta by dz is equal to, this is E, is equal to gamma. Now obviously this equation can be integrated. So I integrate the equation d E d delta by dz is equal to, this is integrated, gamma dz plus a constant of integration. So I get E d delta by dz is equal to gamma z plus c. This is E. Now to find out the value of c, what we do is we say that at z is equal to 0, which means at the point bottommost point P there. Now we go to point P, there is nothing, there is no load acting there. So that there is no deflection also there, in the sense that there is no strain there at that location, because there is no force acting. There cannot be any stress, so there cannot be any strain also. So at that location, at z is equal to 0, d delta by dz is also equal to 0. So we know that from these two, if we feed in the values of z and d delta by dz here in this equation, we get c is equal to 0. Now we write the equation again, we knock off the integration constant, and this equation becomes E d delta by dz equal to gamma z. Now this can be again integrated by rearrangement, gamma by E z. So I integrate over the whole length now. So I say delta is equal to over whole length gamma by E z dz. That is gamma z square by twice E, 0 to L. So that is gamma L square by 2E. That's the answer. This is L. Yeah. So the deflection of the bottom point is the weight density multiplied by length squared over twice of Young's modulus. That's a very important result because it helps us design a lot of structures. It's a very important result in civil engineering. It is helpful in designing those structures which are loaded under self weight. Like for example, trusses which are hanging, bridges, etc. etc. So now we go ahead and see a few more concepts which are very important in strength of materials. Now till now we have seen stress and strain only in one direction, which is along the length of the object. These are called unidirectional problems. But in reality, all the structures are three-dimensional. which means that they have a length, they have a width, and they have a height. So what happens, let's say if I take a beam or a bar, a simple bar, and it is constrained here, and this is loaded with a force. Now what happens is, when it is loaded with a force, it obviously stretches, which means it's after some time its length increases. So this length becomes like this. This is the change in length, delta. So we say that the strain along the length, or what is known as longitudinal direction, is equal to the change in length over original length. This is the original length, L. That is a normal strain which we have studied till now. But it has also been seen that the bar decreases in the other dimensions. So actually the deformation is like this. There is a change in its lateral dimension also. This is the lateral dimension. So if the height was originally h, it becomes less than h. It becomes something like h minus delta. So this is called lateral strain. Now the lateral strain is nothing but the change in its length, which is minus delta, divided by original length, which is h. That is the lateral strain. And Poisson found out that there was a relationship between the lateral and longitudinal strains, which he termed as Poisson's ratio. And the relationship is that the lateral strain, epsilon lateral, is minus times nu of longitudinal strain, wherein this nu is called Poisson's ratio. Now this relationship is true only for isotropic elastic materials, which means that the materials follow Hooke's law and they are isotropic, which means the property values in any direction at any point are same. These materials are called isotropic elastic, and this nu, which is the relationship between the lateral strain and a longitudinal strain, is called Poisson's ratio. Now, Poisson's ratio is a very, very important entity in strength of materials. And why is it important? It's because the Poisson's ratio in a lot of elastic problems is a constant for a given material. So say for example steel, the Poisson's ratio is normally 0.3. For aluminum it is normally 0.33. So it's a constant for various materials, and it's like E, it can be provided as a number. Now we have also seen previously that if we have a load which is acting like this, suppose this is a slab and there is a lateral load acting like this, F, and this area is A, the kind of stress which gets generated here is called shear stress, and that is given by F upon A. Now obviously this thing distorts the slab and it becomes like this. This angle is called shear strain, and it is given by the distortion here, that small change in, or rather that small sideways movement, let's say it is called delta upon height of the slab. Now like Young's modulus, there is another modulus which connects the two entities here. The shear stress is the shear stress and the shear strain. These two are connected by what is known as modulus of rigidity. G is modulus of rigidity. And there is a relationship between E, nu and G for elastic isotropic materials. The relationship is like this, which can also be written as G is equal to E by 2 times 1 plus nu. That's an important relationship to remember, because it tells that E, G and nu are not independent entities, all of them at the same time, for isotropic elastic material like steel. If we are given E and G, we can figure out what is a nu for it. Or if we are given E and nu, we can figure out what is a G for it. But that also tells us an interesting aspect about what is the range of the value of nu. Obviously, nothing, no physical material can have G which is equal to or more than infinity. So if we just put that condition here that G has to be less than or equal to infinity, which is nothing but G is less than or equal to 1 upon 0. If you feed in this value here, we will say E upon 2 times 1 plus nu must be less than or equal to 1 upon 0. So I just rearrange this. So this 0 goes here and this goes here. So that becomes 0 less than or equal to 2 times 1 plus nu, which is nothing but saying that 0 is less than or equal to 1 plus nu, or nu is less than or equal to 1. Sorry, minus 1. I think I have goofed up a bit here. What it says is 1 plus nu has to be greater than or equal to 0. Yeah, which means nu has to be greater than or equal to minus 1. Sorry. Yeah, what this means is that any material has to have nu more than minus 1. So that forms the lower limit for nu. Now, there is another class of problem which is known as three-dimensional problem. So this is like a two-dimensional thing. This was a one-dimensional thing. This is like 1D. This is a two-dimensional thing. So there is a third three-dimensional problem, which is like if we have a brick has all the three dimensions. So it has a length, it has a width, and it has a height. Now again, it has been found out that the change of its volume under a given load, for example, if there's a load, the volume will change, and it has been figured out that the change in its volume over its original volume is also related to the Young's modulus, the Poisson's ratio, and the bulk modulus and the shear modulus. Now, the strain which provides the quantification of change of its volume over original volume, it's also kind of strain. It is called dilatation. Now this is given by the linear strain which occurs in the direction of the application of load into 1 minus 2 nu. That's the relationship, and it's easy to derive. You can derive it yourself. Now this is nothing but sigma upon E 1 minus 2 nu. If this strain or if this dilatation is given in terms of a stress divided by a modulus, the relationship here can be written as this. This factor or this constant is called bulk modulus, or it's given as E equal to K 1 minus 2 nu, or K is E over 1 minus 2 nu. Now you see, this relationship also provides us one interesting limit, or rather a method to figure out a limit on the Poisson's ratio. Obviously the K value has to be again less than or equal to infinity, which means E upon 2 times 1 minus 2 nu has to be less than or equal to 1 upon 0, which means 0 has to be less than or equal to 1 minus 2 nu, or 2 nu has to be less than or equal to 1, or nu should be less than or equal to 1 by 2. So this is the limit on Poisson's ratio, and that's the upper limit. It has to be less than 0.5. From the relationship of E and G, we had seen that the Poisson's ratio has to be more than -1. So it forms a kind of range which says -1 should be less than or equal to nu should be less than or equal to 0.5. Now materials which have Poisson's ratio close to 0.5 are known as incompressible materials. For example, rubber, that's a very incompressible material. Its value of Poisson's ratio is close to 0.49. If we feed in that value here, we will see that the K of rubber is very high number, and it's very unlikely that it can be compressed by considerable or significant amount. So please remember these relationships between the various elastic constants, and E, nu, G and K are called elastic constants. So I will just write it once more. G is equal to E divided by 2 times 1 plus nu, and K is equal to E divided by 1 minus 2 nu. From these two equations, we can of course eliminate either nu or E to write the value of G and K in terms of the third constant. So this in effect ends the basic concepts of strength of materials. From next lecture, we will start seeing very important class of problems which are known as beams. So I request you to please revise all these things before we go ahead and study beams, because these will be very important to remember when we study beams. And beams are very important class of problems because they are heavily used in all static machinery, rotating machinery, moving machinery, and all civil engineering aspects, as well as in aerospace engineering.